So, okay, the title, of course, is just a joke, because at the moment, x86 is the widest used architecture for high-performance computing and in general for server. But my idea is never good if you have only one architecture. So it is better for the market and for the customer to have the possibility to choose between different architecture. And at the moment, except for very big infrastructure, it's not so easy to have it. Our idea is to see and to have a look on different architecture and understand if it is possible to use them in high-performance computing and not only there. We started from market needs and applications area. So what the market is asking now at these days, low power system, highly efficient, something that is alternative to x86 because Intel is covering 95, even more % of the market. Ready for other accelerator if you are in high performance computing market and you work with a lot of computing, probably you are going to use accelerators. And which kind of market are the most interesting from this kind of platform? Of course, high performance computing, web server, Hadoop, oil and gas, image analysis, small computing, if you need something like an appliance close to your workstation, and cloud services. So from that idea, we joined together 3 different companies. Let's say NVIDIA is a supporter. The 2 companies that works on the project, in the real project, are E4, which is an Italian system integrator for high-performance computing and server, and SICO, that comes from the embedded market and industrial market. They are producer of boards. So we joined together, and we are able to start from the design of the board up to the complete cluster, with 2 very small companies compared to the big player in the market. So we started with the first product, and we decided that the basic idea behind something which is high efficient and low cost is a modular server. So you have to use a kind of module embedded with everything inside and use that as the base of everything, because it is embedded, simple, it equips a low power processor, and it is easy to maintain. Actually, all your server is there. It's very small, tiny. If it is broken, you just replace the module. Okay, so we decided to use the Q7 module. It is a standard industrial module. This is my hand with the server on top. So it's a 70 centimeter square system on module. There you have RAM memory, processor, SD, PCI controller, Ethernet controller, SATA, everything. Everything is there. It is a quad core with 2 GB of RAM memory based on ARM solution. But you can have similar module also with Atom or G series from AMD. So actually, the nice thing is if you replace the module, you replace the architecture, and you replace everything. If you want to update your system, replace this, you have a new system. From the experience we had with Q7, at this stage, we decided to stay there because it has enough ports and connections in order to support what we want to do, because you have PCI Express, USB, serial ATA, so everything is there. Of course, there are limitations. One of the limitations of this small module is the power consumption that cannot be more than 12 watts, full load, and the number of the PCI lane. At the moment is 6, but it will increase. Starting from this module, we have created the first board. You can buy on the web, on the SECO website, this board without any box, a complete bare board. The configuration is this. So you have an NVIDIA Tegra 3 ARM Cortex A9 quad-core, which is still an A9 for some months. We will update to A15 later this year. And an NVIDIA Quadro 1000. Why we stay on Quadro instead of Kepler? There is a simple reason. NVIDIA is helping us, actually, NVIDIA is developing the new drivers for ARM. We are the only company that use the NVIDIA drivers for ARM in order to communicating a discrete GPU with the processor. And at the moment, the stable driver support only the old, let's say, old Quadro and Fermi architecture. We have beta drivers, and we are running different kind of GPUs on these boards. You can have a peak performance in single precision of 270 single precision gigaflops. You can also run double precision. Even if ARM is 32 bits, it doesn't mean this that you cannot run a 64-bit application. You have the problem with the processor. If you have part of your application running on the processor, you have problem of performance, as usual. But there's no reason to lock the system to stay in single precision. You can use double, and you have 1/8 of this performance in double, theoretically. Then I will show you later some numbers about the real performance of these boards. We have a limitation also in the network. At the moment, we are working with gigabit. Actually, it is not a big limitation for this board, because this board supports only the Quadro 1000, and the computing power of this board is not so big to reach the performance that you could have, for example, with an InfiniBand. You're not going to saturate any InfiniBand interconnection. Probably you're just using a small percentage of that. But we are working on bigger GPUs and different interconnection in order to increase the computing power and the network of the system. So we decided to box that board with a development microcluster. Previously, we called this Karma. Unfortunately, we had to change name. This is not due to our will. Unfortunately, we had to do it, and from now and for all the presentation and in the future, you will see this new name, ARKA. If formerly you saw the name Karma on the web, we had to replace it. So how it is made, this small box? It is a 5-unit box, but it can be also desktop. You just turn it, and you have 8 blades and a management node, a front-end node. Actually, it is really a microcluster. It comes also configured like a microcluster. Why? Because this release of CUDA we have, 4.2, does not support direct compiling on ARM. So you have to cross-compile your CUDA application in order to be able to run it on the blades. For this reason, we decided to put a small x86 node to do all the front end, all the normal work of a login node, and to do the cross-compiling to run the application on top of the blades. This problem will be solved in the future with the 5.0 release, which will be available in the next months. Configuration is 8 blades and 5 units, 8 CPUs Tegra, 8 GPUs NVIDIA, 2.1 gigaflops maximum performance, 450 watts maximum power consumption, including the management node, and the management node in this case is embedded. Then we have decided to go on with the production of something more stable and reliable, which is a blade chassis with 12 blades in 3 units. This is more common. The chassis probably, you can recognize that this chassis is coming from Supermicro. It's nothing, it's not a strange, but we have replaced everything inside. And we have done this to blade. One blade is called HPC blade, that hosts two different systems, so two CPU and two GPUs. They are discrete systems. There is no communication between these two. And you have to communicate through the internet and the switch. And we also did a solution for data center, which is based only on ARM. So you have 4 ARM in one blade. So this means that you can go up to 48 systems in a 3-unit chassis. And you can put also the local storage in case you need to use Hadoop or an application that needs local scratch. So, a table to summarize it. The high-performance computing version is 12 blade, 3 units, 24 systems with 24 CPU with 24 GPUs, so 24 systems in total, 6.5 teraflops and 1.2 kilowatts power consumption. While the data center one is, again, 12 blades, but with 48 systems. I mean, the GPU R0 and the power, the computing power of this system is, you can, forget it. It's not really important for this kind of application. Of course, the power consumption is incredibly low. So you can have 192 cores running with 350 watts. And you can have a mixed mode, so you can put some blades with only with ARM and some blade with the GPU and ARM processor. Of course, if you want, you can change the ARM. We are now working a lot with ARM because we think that is a good alternative to x86, but of course, we have modules also of Atom, and you can put Atom in case of needs. So market position in an application that we have seen interesting for our machines. Of course, the micro system is for university, finance, and media, most for development. Development is the base for that machine. While for the HPC blade with 12 blades, you can run application on energy, finance, defense, intelligence, telecommunication. There are very good examples in finance that we have seen a lot of good performance. And for the blade data center, web application like MyProduce and Hadoop. How it comes, the system? Actually, the usage of ARM is different compared to the x86. You don't have any BIOS. It is not easy to install. Not all your application would run immediately. You don't have to do a real porting, but you need to work a little bit on compiling. So libraries are changed, compilers are a little bit different. For example, not all MPI runs on ARM at the moment. You have to work a little bit on top. But in any case, you don't need to do a real porting. You need to do a bit of work in order to be able to run it. And for this reason, we have thought, why don't we support and provide all the layer to the customer in order to be ready to run their application. So the system comes directly with Ubuntu installed. Ubuntu is the only stable ARM version of Linux. There is also Fedora, of course, but it is not as stable as Ubuntu at the moment, from our experience. And we had, let's say, a problem of drivers. At the moment, NVIDIA is supporting us only with drivers for Ubuntu. And on top of Ubuntu, we are pre-installing ARM, CUDA for ARM, and MPI. And Toolkit, SDK, Resource and Queue Manager, monitoring tools like Ganglia, the parallel shell, MPI, and some benchmark suite like SHOC in order to see the performance, and a bare metal restore. This is really important because if you have a problem in your system and you need to reinstall it, the procedure is not like I just use a kickstart and reinstall everything. It's not so simple at the moment, for ARM at least. But with the correct recipe and our files, you can do without any problem. Okay, let's see some comparison. So one node from Tegra plus GPU compared to a Sandy Bridge node. I used the same, the same version of GPUs in terms of technology, because if you compare a K20 with a Quadro 1000, the comparison is not really a direct comparison. There are two different technologies level. And first of all, we did some power consumption value. So in idle, our board is 12 watts. And in full load is 48. We did also the GPU and CPU load. While a Sandy Bridge node in idle is around 200 watts, and in full load is 570. This is more or less. I mean, it can be 20 watts more, 20 watts less, depending on the power supply, motherboards, quantity of RAM, and so on. Actually, the percentage of comparison between the node based on ARM and based on Sandy Bridge is this. You have the more or less 6% of the power consumption in idle and more or less the 11% in GPU load. In full load is roughly 8%. So actually a small node is just the 8% of a big Sandy Bridge. Very good, very nice. Let's see about performance, because if the performance is 1/100, there is no reason to go there. These are synthetic benchmarks. We have also some number from real-world application, but it is easier to go with the synthetic benchmark. We have used the SHOC benchmark. Everybody of you, I think, more or less knows this benchmark suite. And these are some of the benchmark we did, only a few of them. So in terms of max flops, single precision, our board is 263. The Intel is 1000. With, let's say, 26% of the power of an ARKA compared to an M2075. If you do the same for fast Fourier transform, you get 14%, 20%, 7%, so on and so forth. So actually it's not so bad, because if power consumption is 8, 9%, and the megaflops you are able to generate compared to an M2075 is at 26%, it should be more efficient. And in fact, if you compare all these results and you just put as a straight line, you normalize the values of a Sandy Bridge like 100%, and you put all the numbers we have seen from SHOC in terms of performance versus price, performance versus density, and performance versus power cost, power consumption, you get very nice number. More or less, you have 2 times more performance in terms of gigaflops per watt, and 3 times gigaflops per dollar. In particular, some of these are really nice. Single precision, maximum performance, reduction of a vector, sorting, matrix multiplication. These are really, really good results. And this is just the beginning of everything. This is our first board. We are working now to many different products, and we are also working to increase the dimension of the GPU and increase the possibility to have a good interconnection, going to 10 gig and InfiniBand. Of course, there is a limitation So not everything is perfect on this system, and the PCI lane that communicates between the ARM processor and the GPU are limited. At the moment, we have only 4 lanes, compared with the 16 Gen 3 of a K20. This limitation cannot be overtaken in any way except with the new ARM architecture. We are looking to the A15 architecture and the 64-bit architecture. With that processor, we will be able to have the full bandwidth between processor and GPU. At the moment, what we can do, it is also to use the GPU direct connection and overcome the problem of copying the data into the memory of the processor and making a GPU communicating with another GPU through GPU direct. This increases performance when you do parallel jobs. Okay, what about the business, which is, I think it will be really interesting for us, but for everybody. The microserver market is growing. It is growing on 200% in 2013 from what they expect. And the worldwide number of microservers sold in the future will rise up impressively. I think this kind of solution based on modules that can be easily replaced and with a very high ratio between performance and power consumption are really one of the future possible architecture. I just want to thank you. I finished my presentation, and stay tuned because next week at the GPU Technology Conference, we will show a very nice machine with a much bigger GPU Kepler into it, and with a different board that you can expand much more this board compared to what I have presented here. But the lunch is next week, I can show you. And thank you again for your attention.